Okay, these are some more problems from section 9.5, and again we just want to test for the convergence or the divergence and specify what test we're using. There's several different tests. Here's number 13. Now remember the nth term test for divergence, if the a sub n diverges, or I'm sorry, the series diverges if the limit is not equal to 0. So this looks like a familiar limit. We've done this before. And the way we deal with this is we're going to let a sub n be this term, n, sine of 1 over n. And if we let t equal 1 over n, so n equals 1 over t. So therefore, as n approaches infinity, that's what we're going to test. We're going to test the limit of this term as n approaches infinity, the sine of 1 over n. So this is our nth term, so we're going to check this out. And then again, we make these substitutions. So as n approaches infinity, t approaches 0. So that makes sense because n approaches infinity, 1 over infinity is 0. Then we can make the substitution. We can rewrite this limit. And again, I'm taking the limit of the nth term, the limit of the nth term. That's going to be the limit. Instead of n approaching infinity, I have t approaching 0. And instead of n, I write 1 over t. And instead of 1 over n, I write t. So I've got this in a form that I'm more familiar with. They're the same. I just use these substitutions, which are all equivalent. And then it ends up with a sine of t over t. And if I substitute a sine of 0, 0, I have 0 over 0, so I can use L'Hopital's rule. If I forget that limit there that we derived, I can use L'Hopital's rule, and I get the limit of cosine t over 1. As t approaches 0, the cosine of t is 1, so I have 1 over 1, which is 1. So since the limit, which is the same thing as this, equals 1, which is not equal to 0, then the summation diverges, okay? And that's by the nth term test for a divergence. So that'd be the nth term test for a divergence. So I wrote it there. I could write it down here again. Okay? And number 14. And again, you can pause these and then look at them and think about them and try to see what motivates us to make these decisions as far as what test we're going to use. Whenever we have a fraction like this, okay, we know if we make the denominator smaller, that will make the fraction bigger. All right? Remember, the bigger the denominator, the smaller the fraction is. So if I make the denominator smaller, this will be bigger, so that I know that right away that this e to the n over 1 plus e to the 2n is less than e to the n over e to the 2n. And I can simplify that quite easily by just reducing, or just dividing. I could say, or putting this on the bottom as e to the negative n, and that would be just 1n. So I know that this is less than this, which equals this, but this is a geometric series, because if I rewrite it as 1 over e to the n, it's a geometric series, and the ratio r is 1 over e. Well, if I take 1 over e, that's about 0.37, which is less than 1, so therefore it converges. So I could say, therefore, that this series converges by the direct comparison test, because I'm comparing it to geometric series. Each term in my original series is less than this, so since is less than this ratio, which is equal to this, so since this series converges, the lesser series also converges, because it kind of forces it down, and that's again by the direct comparison test, or the DCT if you want to abbreviate. That's fine with me. We have a lot of these tests. Okay, let's take a look at number 15. And again, when I see a fraction like this, again, I know that I can make this, if this is going to be, this fraction will be less than this fraction, because here I'm making the denominator, if I make the denominator smaller, that will make the fraction larger. So if I subtract 1 from the denominator, that's going to make it smaller, which will make the fraction bigger. If you add 1 to the denominator, if I add 1 to this, it's going to make it smaller, because I'm increasing the denominator, which makes the fraction smaller. Okay? So hope you can understand this inequality. I can get that from here, especially when I see something like this. It's real easy to get this relationship. And then I can write this in exponential form, and I have this. Now, the only time it's going to work is if the larger series converges. That way it will force the one that's smaller than it also to converge. And if we look at this, this is also, if we look at this 1 over n to the 3 halves, or if we look at the series, the summation of 1 over n to 3 halves, this converges by the p-series test, because p is going to be 3 over 2, which is greater than 1. So since every member of this term, or every member of this series is less than every member of this series, and this series converges, it forces this one down, so to speak. So we can say that this original series converges by the direct comparison test. Okay? So think about those. Okay, number 16. And so these two take a little bit of writing. Okay, this is the summation of 5 n to the third minus 3n all over n squared times n plus 2, n squared plus 5. Okay, now if we look at all the terms, we can see that this is going to behave as n approaches infinity. All these smaller terms, these lesser things will diminish. This will be like 5 n to the third. Then this term isn't that significant. We can factor out, we can show how that works with various number of steps. The 2 will go away. The 2 won't be very significant, and the 5 won't be very significant, so we can actually think of this as n squared, n squared, which is n to the 5th. So this whole rational expression, as n approaches infinity, will behave much like this one, really, because the other terms aren't so significant as we get very, very, very large. Okay, so, and I know that this expression, which I can write as this series, this converges. I can take the 5 out in front, and the 1 over n squared converges by the p-series test, because p is equal to 2. So I can use this as a comparison. So if, I can first of all see that, let's see if these two series behave the same. And if they behave the same, then I know since this series converges, then this has to converge by the limit comparison test. Okay? It's hard to get an inequality on this. We know they behave alike, but it's hard to show that every term here is less than every term here. So let's use a direct comparison test. So we'll take this original series and we'll divide it by, or compare it to this series here. Behaves like this, and eventually behaves like this. So this is a good comparison. So if I invert and multiply, I've got 5 n to the 5th minus 3 n to the 3rd. I guess invert and multiply, so I multiply everything by n squared, multiply the bottom by 5. Now what I did, and you could do this intuitively, you wouldn't have to do this step, but sometimes people have a hard time saying, well, how come this is going to cancel the way it does? Well, what I did was I wrote the top out, and then I actually multiplied the bottom out. It wasn't that bad. I multiplied this trinomial out, this binomial square, binomial times binomial, and I got a trinomial. Well, actually, I got a 4-term method, because I FOILed it out, so I got n cubed, and then I got 5n, and I got 2n squared, and I got 10. So this is 4 terms, and I multiplied each of those 4 terms by 5n squared. This is what I got. 5n to the 5th plus 10n to the 4th plus 25n to the 3rd plus 50n squared. Now, these things you don't really need, kind of like what we did up in the top. This is going to be pretty much like this. But just so you can see, if we remember our little rules for horizontal asymptotes, as n approaches infinity, if we've got a polynomial over a polynomial, we look at the highest degree terms, and if they're the same, we do have a horizontal asymptote, which is a limit. And that's going to be just the ratio of the coefficients of the highest degree terms. In this case, it's 5 over 5, which is 1. Now, by our direct comparison test, if this limit, all right, that I'm comparing to is between 0 and infinity, which 1 is, then these two series behave the same. So if this converges, that converges. If that converges, that converges. If that diverges, that diverges. But we already said earlier that this converges by the p-series test. So since this converges, that also converges. So we can say that our original series converges by the limit comparison test, because we're comparing it to a p-series that does converge, and the limit comparison test gives us that limit as 1, which is in the acceptable range of between 0 and infinity, that tells us that they behave the same way. Okay? So 16 converges by the limit comparison test. So I hope you guys see how that works.